Thank you so much for that introduction. So I had a great experience at the University of Colorado this summer for a 9-week internship with Dr. Tolene's lab, and he is in the Department of Physiology and Biophysics and Otolaryngology. And so today I'm going to present the interaural time difference behavioral tasks using chirps versus clicks. So today I want to teach you that binaural hearing processing occurs within the brainstem. Detecting interaural time differences is a binaural hearing task. ABR, or auditory brainstem response, typically uses a click stimulus, and a newer chirp stimulus can evoke a better response than the original click stimulus. So to give you a background, when we hear sounds, it is an air conduction and it goes through our eardrum and it hits the tympanic membrane and causes a vibration in these bones, a mechanical conduction. And that causes a fluid change movement in the cochlea, which is a fluid conduction, which stimulates chemical conduction in the inner hair cells of the cochlea. And that causes an electrical conduction signal pathway through the nerves, specifically the vestibular cochlear nerve, up into the brainstem first, and then the auditory cortex, where we actually perceive the sound. But today in my presentation, we're going to talk about what happens here at the brainstem level before the sound is perceived. And I wanted to make a special note that this pathway is quite intricate. Like I mentioned, it has 5 different conduction pathways, and so there a lot of things can go wrong in these different processes. So the auditory brainstem response is when they use electrodes and they place it on the scalp and then on the back of the neck as well, and they play a signal and it records a wavelength, a brainstem response. So you can kind of think of it similar to like an EKG. EKG records the electrical responses of the heart, and you can kind of understand what's going on with the heart and diagnose and treat what's going on with the heart based off the electrical signals that are produced from the EKG. And the same kind of reasoning with the electrodes on the scalp, we get these electrical readings. And I want to specifically talk about this diagram here. I want to make sure you guys have a good understanding and background of this. So this here at level 2 is this brainstem slice in this region, and then level 1 brainstem slice in this region. And when we hear the sound from the 8th cranial nerve, or the vestibular cochlear nerve, or the auditory nerve fiber as listed here, it records this peak here at peak 1. And then peak 2 and so forth until the sound is being processed to the inferior colliculus. So here at wave 5 is the region of the brainstem that we believe we understand or perceive binaural hearing, where hearing from both ears is being interpreted, not just one ear. And so this level of the olivary complex, specifically the lateral superior olive and the medial superior olive. And the recordings that we get from the EKG correspond to this 5th wave in blue. And the interesting thing is that when we record these from a binaural hearing, we get something called a BIC. And so this is just my joke. So, you know, the BIC pen, the BIC lighter, that's not the BIC we're looking for. The BIC that we're looking for is the binaural interaction component. So the way we get the BIC is we place the electrodes and then record the sound from both ears, just the left ear, and then record the electrical responses from just the right ear. And so when we add those two together, we get the sum in purple, and it gives us this wavelength. Now, that's different when we play a sound in both ears at the same time, and we get this black line, the binaural sound, electrical recording, and it gives us this black wave. And notice that there's a difference between the binaural hearing and the monaural hearing, electrical wavelengths. And so it's interesting, at the first 4 waves in the lower parts of the brainstem, they cancel out. And if you subtract them, they cancel out. And essentially, the reading's the same. But here at the 5th wave, there's some kind of interaction that's occurring here at this lateral superior olive, medial superior olive, that's saying that the sound the way we perceive sound from both ears is different from the way we perceive sound from just one ear. And so that's how we get this BIC. And so that's what we're looking at. The BIC also, at this 5th wave, they specifically call it a DN1. So there's a 35-year history of literature that has shown that this DN1 is correlated with binaural hearing, and that specifically, when we think of binaural hearing, we think of the way that we're able to localize sound. So I'll explain that. So the interaural time difference is the time that it takes for sound to reach one ear, then the other. We have this thing called the head or face in between our ears, and so there is an interaural time difference. So there's a delay. And so what this does is it allows us to, when the sound first hits this ear, then hits this ear, we're allowed to distinguish the direction of sound or localize sound. And interestingly, this task of binaural hearing is how we're able to understand speech in noisy environments. And so, like in a cocktail party. And so we believe all this is occurring here at this olivary complex, again, similar to this 5th wave of the olivary complex recorded in the ABR. So just want to give you an overview of the cochlea. So when we perceive high frequency sounds, it stimulates the cochlea here at the base. And then when we perceive low frequency sounds, it's when these inner hair cells are innervated at the apex of the cochlea. And so I have a high frequency hearing loss, sensory neural hearing loss. So some of my inner hair cells are damaged here at the base, or sorry, the base of the cochlea. And so I can't hear high frequency sounds. And so that's what my hearing aids do. They help me hear, they amplify the sounds at high frequencies. And so in ABR, they currently use what's called a click. And a click, it plays the sounds all at once, and so it doesn't account for the time that it takes for the sound to travel through the cochlea to the apex. And so I'm going to play the click for you so you know what it sounds like. I'll play it again. So that's what a click sounds like. That's what they use in the ABR so that we hear monaural or binaural hearing. And then that is recorded in the electrode. And so here at high frequencies, you can see in yellow, and then low frequencies here in blue. So what we came up with is the testing of the chirp. And so the chirp is specifically designed so that the low frequencies are played first, and then the high frequencies are played later. So there's a 12 to 16 millisecond delay, or the traveling wave, to reach the apex. And so these low frequency sounds ideally activate, these low frequency sounds take time to reach the apex at the same time that these high frequency sounds are activating the cochlea. And so all the signals are being recorded at once, and so that we get this high electrical recording in the vestibular cochlear nerve rather than a click. And so that was just our theory, and this is what a chirp sounds like. So they did this with an animal study, Dr. Tolene's lab, and they were able to find almost a 2 times better response using the chirp rather than a click in the animals. And so we wanted to test it in humans as well. And so they are currently doing a study with ABRs in humans to see if they can evoke a better BIC with the chirp rather than the click. But my study is kind of like a branch off of that. I only had a few weeks there, so I had to quickly do a project, and so they organized this project. And so my hypothesis when we first started brain skimming the project was that we hypothesized that human test subjects listening to a chirp stimuli rather than the standardized ABR click will more accurately lateralize chirps versus clicks with a given imposed interoral time difference. So we believe that the chirp should better activate the binaural brainstem better, and then with more binaural information available, human test subjects will be able to perform better on an interaural time difference task. So to get the project going, we had to receive IRB approval to work on human subjects. We enrolled our test subjects. We designed the MATLAB program, designed the level-specific chirps, calibrated the auditory equipment. We tested the subjects for about 4.5 hours each subject. And so it's kind of a boring task. So we had to make sure that they were focused and paid attention and did well on the task. So this is the task that they had to do. So this is just an example. So what the task was to select what side they heard the sound on, left or right, and then also to select how far they heard the sound on. So if we manipulated the interaural time differences, that they were smaller and smaller, and so the task got harder and harder, and so the sound would sound like it's coming right under their nose, and they weren't able to localize the sound. And so initially, the test subject would select very far out to the left or very far out to the right, what side they heard the sound on. And so this is just the example. So this is my view as a researcher. So we did a 3 down, 1 up psychometric technique. And so if the test subject got 3 right, the interaural time difference would decrease. This test subject actually did really well. And so if they were doing poorly and they couldn't distinguish left and right well, it'd be in this like 300, 200 microsecond range. Whereas this test subject was able to distinguish sounds left and right pretty easily, and around 10 microsecond interaural time difference. So as you see, she did really well. She got all these correct 3 in a row. And so every time she got 3 in a row correct, it would decrease and the interaural time difference decrease. And then these are the reversals. So every time she got 1 wrong, or if she got 3 correct, it would go down again. And so we took the average of the last 6 reversals and calculated the average interaural time difference. So these are the stimuli that we use, the LS chirp at 10, 20, 40, and 60. And so this is the way the chirp looked. And then we also did the click at 10, 20, 40, and 60. And then we wanted to see if our hypothesis of activating the cochlea with the specific low to high frequencies was accurate. And so we actually did a reverse chirp. So we flipped it upside down. And so we played high frequencies first and then low frequencies. And so we were hoping that this would smear the ABR signal response, and that it kind of showed like the test subject did the worst on the reverse. So we're still processing some of the data, but here is just some preliminary data. So here at 40 dB, we were able to show that the test subject did pretty well on the task up until this 25 microsecond range of this interaural time difference. And then here at 10 dB, they weren't able to distinguish left and right easily at this anything like under 200 microseconds. Whereas with the chirp at 10 dB in comparison, they were able to do better. So the interaural time difference of about less than 75 microseconds, they were able to distinguish left and right a little bit easier, a little bit better with the 10 dB chirp rather than the click. Another thing that, as we increase the volume, the test got easier. And so as we decrease the volume, the task got harder, and it would increase these interaural time differences, the average that they got. So this is the average of the 6 total test subjects and of their thresholds that we received for the last 6 reversals. And so interestingly, so this is just a click. And so, like I said, the 10 dB, they did the worst. It's very hard to distinguish left and right. Now with the chirp, we were able to show that here at 10 dB, the test subject did pretty well compared to the 10 dB click. Whereas the rest of these 60, 40, 20 dB, they did fairly similar. And so it wasn't until the volume was very quiet that they were able to, we believe, activate the cochlea better with the chirp rather than the click. And then we also did a 20 dB reverse chirp. And so this reverse chirp, like we said, they did the worst on this task. And so like we hypothesized. And so they did better with the click and the LS chirp, level specific chirp, and then they did the worst with the reverse chirp, which was flipped backwards, that presented the sound from high to low frequency. So just want to reiterate some of the things I said in the beginning of the presentation. And then I wanted to summarize my conclusions that test subjects lateralized sounds better with an LS chirp at 10 dB, and that test subjects distinguished with a smaller ITD, an LS chirp at 10 dB, and then subjects performed the poorest when presented with the reverse chirp. And again, I just want to reemphasize that the sound is being processed here at the very complex binaural hearing, and hopefully with the chirp, we're able to evoke a larger auditory brainstem response and get a better BIC in the correlating studies. I just want to thank my project contributors and the program that I was associated with over the summer. Thank you so much for your attention today. Does anyone have any questions?